The MD-11 is loud, dirty, and incredibly thirsty for fuel. Passenger airlines gave up on this play way back in the early 2000s. But look at the night sky. It is still swarming with them. Why do the richest logistic companies in the world still cling to technology from the 1980s? The answer lies in the mass. It goes against all common sense, but it makes billions of dollars. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. Mathematics. Capital expenditures versus fuel. Wait, doesn't an old plane like this burn money every time it flies? Let's look at the real difference between owning a plane and flying it. If you wanna buy a brand new Boeing 777 freighter today, the official price is around $352 million. In reality, after negotiations, airlines pay about $160 to $170 million. That is still a huge amount of money. Now let's look at the MD-11. FedEx and UPS were smart. They bought these used planes from passenger airlines for peanuts, maybe $10 or $20 million each. Then they spent about $15 million to convert them into cargo planes. The final price for a ready-to-fly MD-11? Only $25 to $35 million. For the price of just one shiny new Boeing 777, you can buy a fleet of 5 or 6 MD-11s. But what about the gas? It is true, the MD-11 is thirsty. It burns about 20 to 25% more fuel than a modern jet. That is roughly 8,000 kilograms of fuel per hour compared to 6,000 kilograms in a 777. However, unless oil prices explode to $150 a barrel, that extra fuel cost simply doesn't matter. Today, with oil sitting comfortably around $60 or $70, the math is even better. The massive amount of money you save on buying the plane easily covers the fuel bill for years. As they say in the airline business, the best plane is the plane with no monthly payments. The lazy plane factor. Utilization. So why doesn't this math work for passenger airlines? Why doesn't KLM fly old cheap planes? It is because the business models are completely different. To pay for itself, a modern jet must be in the sky for 14 to 16 hours every day. When you fly that much, saving fuel is the most important thing in the world. But cargo is a different game. The life of a FedEx MD-11 is actually very lazy. It usually flies a short trip at night to a major hub, like Memphis or Louisville. It sits on the ground all day long while packages are sorted. Finally, it flies back the next night. In total, it might only fly for 3 to 6 hours a day. Here's the logic. You cannot buy a new Boeing 777 for $170 million and let it sit on a concrete for 18 hours a day. That is a huge amount of frozen money, doing absolutely nothing. But for a cheap older plane, that is fine. If the job involves a lot of waiting on the ground, the cheap MD-11 is actually the perfect machine. The golden mean niche. Load capacity. You might ask, why not just use a different old plane? Well, the MD-11 survives because it has a unique superpower – its size. It fits into a perfect niche that no other older plane can fill. Let's look at the alternatives. First, you have the Boeing 767-300 freighter. It is a great plane, but it can only carry about 53 to 58 tons. For long flights between continents, that is often just too small. On the other side, you have the legendary Boeing 747-400, the jumbo jet. It is a monster that can lift 113 to 120 tons. But here's the problem. Flying a 4-engine giant that is only half full is incredibly expensive. It is overkill. This is where the MD-11 hits the absolute sweet spot. It carries roughly 85 to 92 tons. It holds significantly more cargo than the smaller 767, but it is much cheaper to operate than the massive 747. For specific high-volume routes, like Anchorage to Tokyo or Cologne to Louisville, the MD-11 is not too big and not too small. It is just right. Engineering hell and hole number 2. But it is not all good news. The accountants love this plane. The mechanics absolutely hate it. The biggest headache is the number 2 engine, the one stuck right in the tail. Unlike the engines under the wings, you cannot just walk up to this one. It sits extremely high off the ground. Mechanics need special high-lift platforms just to reach it. Changing an engine on the wing is a standard job, but changing the tail engine is a logistical nightmare. It takes much longer and requires way more effort. And the worst part – spare parts. Remember, McDonnell Douglas disappeared in 1997. No one is manufacturing new parts for this plane anymore. So how do FedEx and UPS keep them flying? They have to cannibalize other planes. They buy old retired MD-11s just to strip them for parts, like vultures. It is the only way to keep the fleet alive. Pilot killer or diva? If the mechanics hate the MD-11, the pilots, well, they respect it, but they also fear it. Some call it the diva, others have darker nicknames. The reason is simple. This plane does not forgive mistakes. Statistically, the MD-11 has a higher accident rate during landings than almost any other modern wide-body jet. You might remember the tragic crashes of FedEx Flight 80 in Narita or Lufthansa Flight 8460 in Riyadh. Both happened right at the moment of landing. Why is it so difficult to land? It comes down to physics. To save fuel and reduce drag, engineers made the horizontal stabilizer, the tail of the plane, smaller than usual. While this made the plane efficient, it also made it less stable. To keep this heavy beast in the air with such a small tail, you have to fly fast. The landing speed, or VREF, is incredibly high, often around 150 to 160 knots, almost 300 km per hour. This is 20 to 30 km per hour faster than similar planes. Everything happens much quicker for the pilots. To help with stability, there is a computer system called LSAS. It is supposed to assign the pilots, but sometimes it behaves unpredictably, fighting against their inputs. The biggest danger is a bounce. If a pilot hits the runway a little too hard, the plane can bounce back into the air. If they try to push the nose down too quickly to fix it, the plane can enter a violent cycle called porpoising. In the worst cases, the nose gear collapses and the plane flips over on its back. It is a powerful machine, but it demands absolute perfection every time it touches the ground. The end of an era. However, nothing lasts forever. The end is finally coming. FedEx has officially announced the beginning of the end. By the year of 2028, they plan to retire their fleet. They are replacing these old Warriors with the smaller Boeing 767 for shorter routes and the massive Boeing 777 for the long hauls. But here is the surprise. They are not killing the MD-11 because of fuel prices. The real killer is maintenance costs. As these planes get older, the engines break down more often. When a plane is stuck in a hangar for repairs, it loses money. Eventually, the cost of fixing it becomes higher than the money you save by owning it. Now I want to ask you, do you miss the era of tri-jets, or do you prefer the efficiency of modern twin jets? Write your thoughts below. If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you next time! Look at this airplane. This is the Embraer E2, also known as the Profit Hunter. With its tech shark livery, it looks like the future of aviation. It is the quietest and the most fuel-efficient narrow-body aircraft in the sky. And for us, the passengers, it is a dream. Why? Because there are no middle seats. It's a 2+2 configuration. No more fighting for an armrest with a stranger. On paper, this plane is a masterpiece of Brazilian engineering. It was supposed to be the giant killer, the plane that would make Boeing and Airbus nervous. It consumes 17% less fuel than the previous generation and has the most advanced fly-by-wire system in its class. But here is the mystery. Airlines are not buying it. While Airbus is celebrating hundreds of orders for its rival, the A220, the Embraer E2 is struggling to find a home. In the world of aviation, being the best doesn't always mean you win. Sometimes you can build the perfect machine, but the market simply refuses to take it. How can a plane that is so right be so wrong? Today we are going deep into the numbers. We are looking at why this tech shark is becoming a headache for investors instead of a gold mine. It's a story of great engines, bad timing, and very expensive legal trap. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. The engine course: innovation versus reliability. To understand why the E2 is struggling, we have to look under the wings. This is the Pratt & Whitney GFT, the geared turbofan. It is a technical miracle, but for many airlines it has become a nightmare. Here is the simple science. In a normal jet engine, the fan and the turbine spin at the same speed. But in the GFT, there is a gearbox. This allows the big fan at the front to spin slower, while the turbine inside spins much faster. This makes the engine incredibly quiet and saves nearly 20% on fuel. For an airline, that sounds like a license to print money. But here is the catch. This technology is extremely complex. The gearbox and the new materials inside the engines are under massive heat and pressure. In the first years of operation, this engine started showing teething problems. We are talking about hardware failures, cooling issues, and parts that wear out much faster than expected. Normally, you fix a part and the plane flies again. But today, the global supply chain is broken. There aren't enough spare parts. Now let's look at the math. In the first year of a new aircraft's life, you expect it to be in the air 10 or 12 hours a day. But many E2 operators found their planes stuck on the ground for months, waiting for engine repairs. If we compare the E2 to the older E1 during their first years, the dispatch reliability, which is how often the plane is ready to fly on time, was significantly lower for the new model. Airlines hate uncertainty. When a CEO looks at the E2, they don't just see a fuel-efficient jet, they see a risk. They ask, will this plane fly tomorrow, or will it sit in a hangar because of a broken gear? For many, the 20% fuel saving isn't worth a plane that cannot fly. The legal trap. How unions grounded a giant. But wait, if the engine is the only problem, Embraer could just fix it, right? Wrong. The biggest problem for the E2 is not mechanical. It is a legal trap called scope clauses. To understand this, we have to look at the United States, the biggest market for regional jets in the world. In the US, major airlines like United, Delta, and American don't fly their own small planes. Instead, they hire regional airlines to do it for them. But here is a very strict contrast between the big airlines and their pilot unions. This contrast is the scope clause. It says, you can use regional pilots, but only if the plane stays under a certain size and weight. There is one specific number that killed the E2. 76,000 pounds. That is the maximum takeoff weight, MTOW, allowed for regional jets in America. The older Embraer E175 fits this rule perfectly. It is the king of the US skies because it weighs exactly what the union allows. But the new E175 E2, because of those big heavy fuel-efficient engines and those advanced wings, it weighs nearly 89,000 pounds. It sounds crazy, doesn't it? Embraer built a plane that is better, cleaner and more quiet, but because of a piece of paper signed by lawyers and unions, it is too heavy to fly in the US. The unions refuse to change the weight limit. They want to protect the jobs of pilots who fly the bigger mainline jets. They fear that if they allow heavier regional planes, the big airlines will stop using large jets and replace them with smaller ones. Embraer made a massive gamble. They believed the rules would change by the time the E2 was ready. They were wrong. The rules stayed the same, and now the E175 E2, the most important version of the plane, has 0 customers in the world's most profitable market. It is a tragedy of modern aviation. You can spend billions of dollars on engineering and create a masterpiece, but you can still be defeated by a single line of text in a legal contract. The shadow of Airbus, a David versus Goliath battle. Now imagine you are a CEO of a mid-sized airline. You need a new jet. You look at the Embraer E2, but then you look at its biggest rival, the Airbus A220. And this is where the shadow of the giant falls over Embraer. The A220 was not always an Airbus. It started as the Bombardier C series, a brilliant plane from Canada. But Bombardier almost went bankrupt building it. Airbus stepped in and used its massive global power to turn it into a superstar. How does Airbus win? It's simple. They are a one-stop shop. Airbus has deep pockets and a huge family of aircraft. When they talk to an airline like JetBlue or Delta, they don't just sell one plane. They can say, if you buy 50 of our big A321s, we will give you a massive discount on 20 small A220s. Embraer cannot do this. They are a smaller independent company. They have to make a profit on every single jet they sell. They cannot play the same money game as the giant like Airbus. The numbers tell a painful story. Airbus has over 800 orders for the A220. Embraer? They have around 200 for the E2. In the business world, success creates more success. Airlines see everyone else buying the A220, so they feel it is a safer investment. But there is one more secret weapon Airbus has – the pilots. If an airline already flies the Airbus A320, the most popular plane in the world, it is much easier to train their pilots to the A220. It feels like a part of the same family. If they buy the Embraer, they have to build a completely new department for training and maintenance. For many airlines, even if the Embraer is a slightly better technical machine, the Airbus is the better business decision. Embraer is fighting a war against a company that has more money, more influence, and a bigger family. It is a fight that is almost impossible to win. Global survival. Looking for a new home. So, is the E2 dead? Not exactly. Since the US market is blocked by legal rules and Europe is dominated by Airbus, Embraer is looking at the rest of the world. In places like Brazil, India, and Southeast Asia, the scope clause doesn't exist. These regions have thousands of islands and growing cities that need a plane exactly like the E2. Something bigger than a small turboprop, but smaller and cheaper to run than a massive Boeing 737. But the most important test is happening right now, in Canada, with Porter Airlines. Porter is the hero of the E2 story. They didn't just buy a few planes, they ordered up to 100 of them. They are using the E2 to fly long distances, like Toronto to Los Angeles or Florida. Porter is essentially a living laboratory. If Porter can prove that the E2 is reliable, that the engines stay healthy, and that passengers love the 2+2 seating, other airlines will stop being afraid. Porter is the advertising face that Embraer desperately needs. If Porter succeeds, the E2 survives. If Porter struggles, E2 may stay a niche aircraft forever. However, Embraer is smart. They are already preparing a plan B. They know the E2 might never be a global bestseller like the E1 was. So they are moving into a new space – sustainable aviation. While Boeing and Airbus are fighting over big jets, Embraer is designing a new generation of green planes. They are working on high-tech turboprops and even electric aircraft under their Energia project. Their strategy is simple. If you can't beat the giants in the jet market, leads the way in the green market. Embraer isn't giving up. They are looking for every gap in the market that the giants have missed. They are betting that the future of flying isn't just about being big. It's about being smart, efficient, and ready to pivot when the world changes. Now I want to ask you, would you prefer the Embraer E2 over Boeing or Airbus? And what do you think about this company in general? I'd be interested to hear your opinion. If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you next time. Picture this. You are standing on a tarmac and right in front of you is a machine so impossibly massive that you could literally pack the entire fuselage of a Boeing 737 inside its outer shell, with room to spare. We are talking about a machine that breathes in tons of air every single second, squeezes it with 60 times the pressure of our atmosphere, and burns it at temperatures that would effortlessly melt ordinary steel. This is the GE9X. It is undisputed heavyweight champion of the skies, built specifically for the Boeing 777X. But the story of this engine isn't just about making things bigger. It's about a crazy paradox where the world's most powerful engine actually uses less brute force in its daily life than its predecessor. It's about custom-engineered pixie dust, 3D printing metal, and pushing the literal laws of thermodynamics on the absolute edge. Before we tear into the guts of this absolute monster, if you enjoy deep dives into the bleeding edge of aviation technology, do me a huge favor. Hit that like button and make sure you are subscribed. It takes just a second, but it really helps push these discussions out to more people. So let's talk about the sheer scale of this thing, because numbers on a screen really don't do it justice. The front fan alone measures 134 inches across. That is almost 11.5 feet of just fan blades. Once you wrap the nacelle, that's the outer housing, around it, the total width comes out to 184 inches. Like I said, a standard Boeing 737 fuselage is only about 148 inches wide. You could slide a 737 right through the engine pod of a GE9X. But here is where it hits out first really fascinating paradox. Because it's so huge, everyone naturally assumes it just blasts out more thrust than anything else in the sky. All day, every day. And technically, yes, it holds the Guinness World Record. Back in November 2017, on a test stand in Peebles, Ohio, GE engineers pushed this thing to a staggering 134,300 pounds of force. To put that in perspective, the fighter jets you see breaking the sound barrier usually max out around 30,000 to 40,000 pounds of thrust. The GE9X crushed the previous world record, which was held by its older brother, the G90. But if you look at the actual certification documents for daily commercial flying, the GE9X is only certified to operate at 110,000 pounds of thrust. The older GE90 actually operates at over 115,000. Why? Why build the biggest, most powerful engine in human history, only to throttle it back for everyday use? The answer is efficiency. The Boeing 777X is a highly aerodynamic aircraft with a massive glider-like wingspan. It doesn't actually need to muscle its way through the air with brute force like older jets. By building a larger fan but running it at a slightly lower thrust rating, GE dramatically increased the bypass ratio. Let's break down what that means. Because bypass ratio is the secret sauce of modern jet engines. The GE9X has a bypass ratio of 10:1. That means for every 1 unit of air that goes into the fiery core of the engine to be compressed and ignite, 10 units of air bypass the core entirely. They are just pushed around the outside of that giant 134-inch fan.
That bypass air provides the vast majority of the thrust. And because there is so much bypass air, it creates this massive, relatively cool stream of air that wraps around the superheated, supersonic exhaust shooting out of the core. That shield of air actually acts as a muffler. So despite being the largest engine ever built, GE officially stated that per pound of thrust, the GE9X is the quietest engine they have ever produced. Now, moving that much air requires a very special type of a fan. If you look closely at the front of the GE9X, you'll notice it only has 16 fan blades. You would think a bigger engine needs more blades, but aerodynamics is a funny thing. Fewer blades mean less weight and less aerodynamic drag. But to make 16 blades do the work of 22, they have to be incredibly wide and perfectly shaped. These blades are made of 4th generation carbon fiber composites. They are incredibly stiff, but pure carbon fiber has a problem. It can be brittle. If a large bird strikes a purely carbon fiber blade at 500 miles an hour, it could shatter. So GE engineers added steel leading edges to slide through the air and deflect impacts. And they used fiberglass for the trailing edges to give the blade just enough flexibility to absorb a shock without snapping. But getting this massive fan off the ground presented a massive headache before the engine ever even made it to a Boeing aircraft. Whenever a company builds a new engine, they have to fly it on a testbed plane first. General Electric usually uses a heavily modified Boeing 747. But when they wheeled the GE9X out to their 747-100 test plane, they realized the engine was so ridiculously big that it would literally scrapple the runway. They had to upgrade their test bed to a Boeing 747-400, which sits slightly higher. Even then, Boeing had to engineer a completely custom pylon to attach it to the wing, and they had to tilt the entire GE9X upward by 5 degrees compared to the other 3 engines on the plane, just to give it enough ground clearance during takeoff and landing. Imagine looking out the window of a 747 and seeing one engine that is twice the size of the others, tilted slightly toward the sky. That is what it took just to test this thing. Once the air gets past the giant fan, we enter the core, and this is why the GE9X sounds like the pure science fiction. To get the maximum amount of energy out of a drop of jet fuel, you have to squeeze the air as tightly as possible before you ignite it. The GE9X has an overall pressure ratio of 60:1. The air entering the combustion chamber is compressed to 60 times the pressure of the outside atmosphere. It is violently squeezed through an 11-stage high-pressure compressor. By the time fuel is injected, the air is practically a solid wall of energy. But when you squeeze air that tight and burn it that efficiently, you generate an ungodly amount of heat. The inside of the GE9X reaches temperatures of 2400 degrees of Fahrenheit. That is roughly 1315 degrees Celsius. Normally, engineers solve this by bleeding off some of the cool air from the compressor and channeling it through tiny holes in the turbine blades to keep them from melting. But bleeding off air means you lose efficiency. So GE completely changed the materials. They heavily utilized ceramic matrix composites, or CMCs, in the hottest part of the engine. CMCs are made of silicon carbide ceramic fibers embedded in a ceramic resin. They are 1/3 the weight of metal, twice as strong, and most importantly, they can brush off 2400 degree heat without breaking a sweat. Because they can handle the heat natively, the engine needs 20% less cooling air. That air stays in the main flow path, generating more thrust and burning less fuel. And it's not just ceramics. The GE9X represents a massive shift in how engines are physically manufactured. It features over 250 parts that are additively manufactured. That's a fancy way of saying 3D printed. But we aren't talking about desktop plastic printers. We are talking about electron beam melting, where a high-powered beam fuses layers of titanium aluminate powder micron by micron. The low-pressure turbine blades are 3D printed. The fuel nozzles are 3D printed. By printing these parts, engineers can design complex internal cooling channels that are physically impossible to cast or forge using traditional metalworking. And because they are printed as a single piece, there are fewer welds, fewer joints and less weight. But none of this high-tech wizardry matters if the engine breaks down in the real world. And the real world is incredibly harsh. A huge portion of the orders for the Boeing 777X are coming from Middle Eastern airlines like Emirates and Qatar Airways. These planes are going to be spending thousands of hours flying over expansive deserts, sucking in fine sand and dust. If sand gets into a 2400-degree engine core, it melts into glass, clogs the cooling holes and destroys the engine. GE couldn't just wait and see what would happen, so they went to extreme lengths. They literally hired PhD-level geologists to analyze the exact chemical makeup and consistency of the airborne dust found at cruising altitudes over the Middle East. It's incredibly fine, almost like talcum powder. Back at their testing facility in Ohio, they built a bespoke rig that blasted this custom engineering dirt directly into the core of a running GE9X for thousands of simulated flight cycles. They intentionally tried to choke their own masterpiece to death, just to prove that the 3D printed nozzles and the CMC components could survive the harshest environments on the Earth. When you put all of this together, the 134-inch fan, the 10-to-1 bypass ratio, the 60-to-1 pressure ratio, the 3D printed titanium, and the ceramic composites, you get an engine that is a full 10% more fuel efficient than the G90, while producing 50% fewer NOx emissions than current regulations require. The G9X isn't just a bigger engine, it is a fundamental shift in how we move massive amount of weight through the air. As the Boeing 777X finally gears up to enter commercial service, it is going to be riding on the back of an engineering marvel that redefines what is possible in modern aviation. If you made it this far, I really hope you enjoyed this deep dive into the mechanics of the GE9X. Let me know down in the comments what part of this engine blows your mind the most. Is it the 3D printing, the size of the fan, or that crazy pixie dust test? And of course, if you haven't already, please drop a like on the video and subscribe to the channel, so you don't miss our next deep dive into the machines that connect our world. Thanks for hanging out, and I'll see you in the next one.
Do you know how airline CEO choose between B787 or A350? It is pretty obvious that they don't just compare how many passengers plane can carry or how far they can go. Even savings on fuel are not always a deal breaker. So today I won't do this. Instead, let's look at the exact hidden specs, which look really insignificant to an ordinary aviation fan, but they make a huge difference to the airline CEO. But first, hit the like and subscribe button. This is a super simple action, but I really need your support. For me, it is vital. Thank you. Chapter 1. The strategic bet. Frequency versus capacity. Let me start from the explanation why this comparison even makes sense. Some can say that the Airbus A350 is actually closer to the Boeing 777 than to the 787. And they will be right, exactly in the case of the A350-1000 version. But others can argue that A350-900 is not a direct competitor to the 777, and especially 777-9. It is much closer to the Boeing 787-9 or 10, and they will be also right. But from the third point of view, the A330neo is closer to the Boeing 787 than the A350, and this also makes sense. So, what I wanna say that manufacturers have the right version of the airplane to compete in the majority of niches, but none of their models are the pure rivals in every version. All of these comparisons make sense, but in different videos. If you wanna see some of them, let me know in the comments below. Anyway, let's get back to our main heroes, the Airbus A350 and the Boeing B787. Look, here is the thing. When Boeing sat down to design the 787, they were literally betting the house on a concept called fragmentation. They sort of predicted that era of massive hubs was ending. They figured passengers didn't want to connect in huge airports anymore. They wanted to go straight up to point, like from Osaka directly to Sanjus. To make that work, you need a plane that is cheap to run even if it is not totally full. And this brings us to the first massive difference. To be honest, for the 787, the most critical metric is trip cost. Basically, the 787 is lighter and smaller. It is optimized for around 290 passengers. It is designed to minimize risk. I mean, if you can only sell 200 tickets, on a big plane you are losing money. But on a 787, you might actually break even. So it's kind of a safety net for the airline's bank account. On the other hand, Airbus was playing a different game. Seriously, the A350 XWB was a direct attack on the Boeing 777 market. They focused on hub-to-hub routes with high demand. Mind you, the A350-900 is bigger. It holds about 325 passengers, which is like 30 or 40 more seats than the Dreamliner. Fair enough, the A350 costs more to fly than a 787. It burns more fuel per trip, no doubt. But here is the trick. If you can fill those extra seats, the A350 actually prints more money per passenger. It is all about CASM, cost per available seat mile. It is a volume game. You know what I mean. And listen, this leads to a hidden spec that almost nobody talks about, but CEOs check it immediately. Maximum takeoff weight, or MTOW. The 787-9 is sitting at around 254 tons. The A350-900, it is a beast at 283 tons. For real, that is massive. Well, airports charge you landing fees based on weight. So if you buy the heavy A350 and fly it half empty, you are literally burning cash on fees and fuel for structure you don't need. That's a nightmare. But at the end of the day, if you have a slot-constrained airport like London Heathrow, where you can't just add another flight, you need that extra capacity. In that case, the A350 is probably the better option. Chapter 2. The barrel versus the panel. The repair nightmare. Okay, listen, let's talk about what these things are actually made of. We all know that both planes are pretty much plastic. Well, carbon fiber reinforced polymer, or CFRP to be precise. But the way they build them, it is totally different. And this difference is low-key terrifying for the maintenance managers. Look, Boeing went full sci-fi with the 787. They decided to make the fuselage sections as one giant solid piece. It's called a one-piece barrel. They literally spin carbon fiber tape around a huge mold. No rivets, no joints, just one smooth tube. It saves like 20% weight compared to aluminum, which is huge. But here is the thing. What happens when a catering truck accidentally hits the side of the plane at the airport? It happens, you know? If you dent a traditional aluminum plane, you just rivet a patch on it. But on a 787, it is a nightmare. Seriously. You can't just cut a hole and plug it. You have to do a process called scarfing. You have to sand down the damaged layers circle by circle, apply a patch, put it under a vacuum, and heat it with a special oven right there on a tarmac. It is super complex work. I mean, if the damage is bad enough, your shiny 787 could be stuck on the ground for weeks. For a CEO, having a plane that can't fly is straight up losing money. Now look at Airbus. They saw what Boeing was doing and said, I don't think so. For the A350, they choose a panel-on-frame approach. It is basically 4 huge carbon panels, top, bottom and 2 sides, bolted onto a carbon frame. It sounds less cool, I guess, but it is way smarter for repairs. If that same truck hits the side of an A350, it is fair enough to say the repair is much more straightforward. You are dealing with the panel, not the structural integrity of the entire tube. It is kind of like Legos compared to Boeing's pottery. Chapter 3. The heart and lungs. Engines and the bleed war. Look, the fuselage is cool and stuff, but the real revolution is happening inside the systems. And honestly, this is why Boeing and Airbus went in totally opposite directions. It is called the bleed air war. Basically, on a normal plane, the engines provide thrust, but they also do something else. The plane literally steals hot, high-pressure air from the engine compressors to run the air conditioning, pressurize the cabin and de-ice the wings. This is called bleed air. Well, for the 787, Boeing said, we are done with that. The 787 is the first commercial, more electric aircraft. They straight up removed the heavy pneumatic ducts and valves. Instead, they installed massive electrical generators on the engines. I mean, we are talking about 1 megawatt of power generation on board. That is enough to power a small village, no doubt. Well, bleeding air from the engine kills efficiency. By going electric, Boeing saves like 3% on fuel. That is huge. But here is the thing. This makes the 787 electrical system incredibly complex. You remember the early battery fires? That was the price of innovation. And for mechanics, fixing high voltage systems is high-key dangerous if you aren't careful. Airbus? They looked at this and said, too risky. So the A350 actually kept the traditional pneumatic system. It still uses bleed air. It is conservative, I guess, but it is super reliable. Mechanics know how to fix it because it is pretty much the same technology they have seen for decades. And then there are the engines themselves. The A350 is exclusive to the Rolls-Royce Trent XWB. And to be honest, this engine is a masterpiece. It uses a 3-shaft design, which is unique to Rolls-Royce. It allows the compressor to spin at crazy 50-to-1 pressure ratio. It's legit the most efficient large aero engine flying today. And unlike the Trent 1000 on the Boeing 787, which had those nightmare issues with cracking blades, the XWB has been rock solid. On the other hand, the 787 gives you a choice, and most airlines pick the General Electric GE9X. Why? Because it uses composite fan blades. They are carbon fiber, not titanium. This makes the engine lighter by like 400 or 500 kilograms. That is half a ton of free cargo you can carry, literally. Or $2,000–$5,000 of extra revenue every flight. So what does this mean for the numbers? If you look at the specific fuel consumption per passenger, the 787-9 sits around 2.31 liters per 100 kilometers. The A350-900 is around 2.39 liters. It looks like a small difference or whatever, but over the life of a plane, the 787 is just slightly more efficient at sipping fuel per trip. But remember, the A350 carries more people, so it balances out. Chapter 4. The Office. Flight Options and Philosophy. Honestly, this is where the difference between Boeing and Airbus stops being about engineering and becomes almost religious. Here's the thing. The philosophy of how you fly these birds is totally opposite. Airbus uses something called heart protections. On the A350, the computer is literally the boss. I mean, if you can pull the side stick all the way back, and the computer will just say, no, it won't let you bank past 67 degrees, it won't let you stall, it keeps you inside the safe envelope period. Boeing? Well, they have a different view. The 787 uses soft protections. The computer will warn you, it will put resistance on the yoke, like fighting you back, but at the end of the day, if you pull hard enough, the plane will let you do whatever you want, even if it breaks the plane. The pilot has the final word. So which is better? I guess it depends on who you ask. But for the CEO, there is another acronym that matters way more than flight philosophy: cross-crew qualification. Listen, training pilots is expensive. Low-key, it is one of the biggest costs for an airline. If you already have a fleet of A330s, which tons of airlines do, retaining a pilot to fly the A350 takes just 8 days. Seriously, 8 days. It's called a reduced type rating. They can even fly both planes at the same time. For the Boeing 787, even if you are coming from the 777, the transition takes like 15 to 20 days. It is nearly double the time. Mind you, paying for hotels, simulators and instructors for an extra 2 weeks for hundreds of pilots, that is literally millions of dollars in savings for Airbus operators. And then there is the tech right in front of your face. If you jump into a 787, you will see the Duel head-up displays, HUDs, as a standard equipment. It looks like a fighter jet. You can land in fog without ever looking down. It's pretty much the coolest toy in the industry. The A350? Well, it focuses on screens. Massive 15-inch displays. It feels like a flying IT center. HUDs are usually just an option, however the popular one. Chapter 5. The passenger experience. The wits lie. Now let's go back to the cabin. Honestly, this is where the marketing brochures usually hide the ugly truth. I call it the wits lie. You know, the A350 is called XWB. That stands for extra wide body. Let's look at the raw numbers. The cabin width of the A350 is 5.61 meters. The Boeing 787, it is 5.49 meters. So the difference is basically 12 centimeters. You might think, 12 centimeters? Who cares? That's like a length of a phone. But here is the thing. In the world of economy class, 12 centimeters changes everything. See, when Boeing designed the 787, they kind of envisioned it with 2-for-2 configuration. In that layout, it is super comfy. But airlines love money, right? So pretty much every major airline squeezed a 9th seat in there. The seats on a 787 are typically 17 inches wide. Seriously, if you are a normal-sized human, your shoulders will be touching the person next to you. It is tight. Airbus, on the other hand, designed the A350 for 333 seats from the day one. That extra cabin width means you get a standard 18-inch seat. Look, 1 inch doesn't sound like much, but on a 14-hour flight, it is the difference between sleeping and suffering. If you value your personal space, you literally want the Airbus. Now regarding the air you breathe, it is a draw. Because both planes use composite fuselages, they can handle higher pressure. So instead of the typical 8,000 feet cabin altitude, both the 787 and A350 keep it around 6,000 feet. This means more oxygen in your blood and fewer headaches. Totally a win for everyone. By the way, we have to talk about the windows. The 787 has those famous electronic dimmers. No physical shades. It looks futuristic and stuff, but they don't block 100% of the light. If the sun is shining directly on your window, it still gets sort of bright and hot. The A350 is stuck with traditional pull-down shades. It is old school, fair enough, but when you close it, it is actually dark. However, in the case of Airbus, some airlines have also chosen an option of electronic dimmers. Chapter 6. The belly. Cargo and liquidity. Okay, passengers pay the bills, but cargo. Cargo is pure profit. Honestly, this is the hidden battleground where the A350 high key shines. If you look at the spec sheet for the standard versions, the 7879 and the A350-900, they both fill exactly 36 cargo containers, LD3s. So it looks like a tie, right? Well, not exactly, because there is a trap called payload range. Here's the thing. On a medium flight, sure, both planes can take a full load of passengers and a full belly of cargo. But what happens when you fly super long distances, like San Francisco to Singapore? On those ultra-long range routes, the Boeing 787 hits its maximum takeoff weight limit faster. It has to leave cargo behind to carry enough fuel. The A350 with that massive 283-ton weight limit we talked about earlier, it keeps lifting. Actually, on those extreme routes, the A350 can carry like 5 tons more cargo than the 787. Think about it. 5 tons of high-priority freight, iPhones, pharmaceuticals, whatever. That is thousands of dollars per flight. For a CEO, that extra cargo revenue basically pays for the fuel and the crew. It is literally free money. But wait a minute. There is one final financial spec. The asset value. To be honest, the 787 is the liquid king of widebodies. Boeing has built over 1100 of them. They are everywhere. It is super easy to buy or sell one quickly. But here is the thing. Boeing Common isn't always best for the bank account. If you look at the market numbers for 2025, the A350 actually wins on value. An A350-900 brings in like 1.25 million a month in lease payments. The 787-9, it is sitting lower at around 1.10 million. So even though the A350 costs more to buy, it holds its value better. Analysts say it has better residual value stability, because the market isn't flooded with them yet, and demand is high. Basically, for a CEO, the 787 is a liquid asset you can flip fast, but the A350 is a stronger asset that generates more cash every single month. Conclusion and verdict. Look, theory is cool, but let's see how this actually plays on the real world. Why do airlines really choose one over the another? Take Delta Airlines. They operate both. Actually, it makes perfect sense. They use the A350-900 as their flagship for heavy routes across the Pacific. But for routes that are a bit thinner, like New York to London, the A350 is too big and heavy. So they ordered the Boeing 787-10. It fits perfectly in the middle. They literally use the right tool for the right job. Then look at Singapore Airlines. They fly the longest flight in the world, Singapore to New York, 18 hours. They choose the A350-900 ULR. Why? Because, as we discussed in Chapter 6, the 787 hits a weight limit on those extreme ranges. The A350's fuel system allowed them to fly the distance and still make money. No doubt, Airbus won that niche. And finally, Emirates. This is where it gets spicy. They ordered 50 A350-900. Why? Because the Rolls-Royce XWB engine proved it can handle the desert heat and sand. Mind you, they are still fighting with Rolls-Royce about the bigger engines for the A350-1000, complaining about maintenance costs. But for the 900, they trusted more than the early engines on the 787. So in the desert, reliability was the deal breaker. So here is the final verdict. Choose the Boeing 787 if you want to open new routes between smaller cities, point to point. You want the lowest possible cost per trip to minimize risk. You need a liquid asset that is easily to buy and sell. Choose the Airbus A350 if you are replacing big Boeing 777s and fly between major hubs. You have a bunch of A330 pilots and want to save millions on training. You need that extra cargo capacity on super long flights. You want the passengers to love you for those 18-inch seats. At the end of the day, it is not about which plane is better. The 787 is a surgeon's scalpel, precise and efficient. The A350 is a Slitgehammer, powerful and capable. Anyway, both work if you know what you are doing. Which one would you choose if it was your money? Let me know in the comments below. And if you enjoyed this deep dive, please hit that like button. It really helps the channel. Don't forget to sub. See you in the next one.
Ever wondered why airlines basically turned their backs on the Airbus A380, yet they are still lining up for the Boeing 777X, even though it is nearly 7 years late? Now, I'm not talking about the usual "it's too big" argument. I'm talking about the hidden specs. For instance, did you know the A380 would be 15% more fuel efficient today if Airbus hadn't gambled on versions that were never ever built? There is a lot of engineering drama behind these two jets that rarely makes the headlines. You will want to see this. And hey, if you find this breakdown interesting, hit the subscribe button. It really helps a small creator like me to keep digging into these stories. Let's get into it. Infrastructure integration and geometric constraints. Firstly, let's start with those fancy wingtips on the 777 and look at what they really give to the airlines. The most significant operational hurdle for ultra-large aircraft is their interaction with existing airport geometry. The Airbus A380 was famously designed to fit within an 80-meter by 80-meter box, a constraint that dictated every major aerodynamic decision. The A380-800 is a permanent ICAO Code F Group 6 aircraft. This designation requires airports to provide runways with a minimum width of 60 meters and taxiways with a minimum width of 23 meters, along with significantly increased separation between parallel taxiways and runways to prevent wingtip collisions. The global adoption of the A380 necessitated billions of dollars in infrastructure upgrades, from strengthening bridges to installing specialized dual-level jet bridges. These costs acted as a massive entry barrier, effectively limiting the A380 to approximately 60 to 80 major global hubs. The Boeing 777-9 approaches this problem with a geometric dual identity. During flight, the wingtips are extended to a span of 71.8 meters, placing it in the same Code F category as the A380, for airside operations such as takeoff and landing. So what I mean? The 777X also require runways with a minimum width of 60 meters. However, upon exiting the runway, the outer 3.5 meters of each wing fold vertically, reducing the wingspan to 64.8 meters. This allows the 777-9 to operate as a Code E Group 5 aircraft on the ground, even loops as the Boeing 777-300ER and Airbus A350-1000. The 777-9 is notably longer than the A380, making it the longest passenger airliner ever produced. This length presents its own challenges for gate depths, but the folding wingtips eliminate the need for the lateral space expansions that the A380 demanded. Maneuverability and ground operations. The hidden complexity of ground maneuvering lies in the minimum turning radius and the 180-degree turn capability. The A380, despite its mass, achieves a surprisingly tight turn width of 50.91 meters, but only through the use of differential braking and asymmetric thrust, Techniques that increase the tire wear and engine stress. The 777-9 requires a wider 59-meter pavement width for a standard U-turn without differential braking. A critical deal breaker for the A380 in ground operations is its turnaround time. Due to its double-deck configuration, the A380 requires specialized catering trucks and cleaning crews that can access both levels simultaneously. A typical long-haul turnaround of an A380 takes approximately 180 to 210 minutes, whereas the 777-9 is targeted to achieve turnarounds in 90 to 120 minutes, significantly improving aircraft utilization rates. Aerodynamic architecture and wing physics. The divergent philosophies of Airbus and Boeing are most apparent in the wing design. The A380 wing was over-engineered for a larger Dash 900 stretched variant that was never built, resulting in a wing area that is excessively large for the current Dash 800 model. Aspect ratio and induced drag penalties. The aspect ratio, AR, of a wing is defined as the square of the wingspan, B, divided by the wing area, S. For the A380, the AR is approximately 7.5 to 7.8, which is significantly lower than the 9.0 to 9.5 found on the newer twin jets like the 787 and A350. This low aspect ratio is a direct consequence of the 80-meter wingspan limit. To provide enough lift for a 575-ton aircraft within that span, engineers had to increase the wing chord, leading to a massive wing area of 845 meters squared. The aerodynamic penalty is severe. Induced drag due to weight, accounts for a 50% of total drag at cruise, which is 10% higher than it would be with an optimal 90-meter wingspan. The 777-9, by utilizing carbon fiber reinforced polymers CFRP and folding wingtips, achieves an aspect ratio of approximately 11.04. This slender wing generates lift much more efficiently and allowing for a higher cruise speed of Mach 85 compared to the A380's economical Mach 83. Wing loading and thrust-to-weight ratios. Wing loading, W divided by S, is a critical metric for takeoff performance and cruise efficiency. The A380 has a relatively low wing loading at MTOW due to its oversized wing, while the 777-9 operates at much higher pressures. The higher thrust-to-weight ratio of the 777-9, powered by the massive GE9X engines, allows for superior climb gradients and better performance in hot and high conditions. The A380, while powerful, is hampered by its massive empty weight, which is nearly 10,000 kilograms heavier than the 777-9. Propulsion systems. GE9X versus the quad-engine paradigm. The propulsion system is perhaps the single most important deal breaker in the comparison. The A380 utilizes 4 engines, from either the Engine Alliance GP7200 or Rolls-Royce Trent 900. These engines represent late 1990s technology, which was quickly eclipsed by the GE9X and Trent XWB generations. Thermodynamic efficiency and the GE9X. The GE9X is the largest and most powerful commercial engine ever built, featuring a 134-inch fan and 27:1 compressor pressure ratio. It offers a 10% reduction in specific fuel consumption, SFC, compared to the GE90-115B. and a nearly 20–25% improvement over the engines powering the A380. One hidden specification is the engine weight fraction. On the 777-9, the two GE9X engines represent a smaller percentage of the MTOW than the four engines on the A380, despite the GE9X's massive size. This is because the twin-engine configuration eliminates the need for two extra pylons, dual fuel lines, and complex quad-engine synchronization systems, engine maintenance cycles, and durability issues. A significant deal breaker for the A380 is the sheer cost of engine maintenance. With four engines, an airline faces twice as many shop visits as a twin-engine operator. Engine maintenance for an A380 can reach $30,000 per flight hour, whereas a 777 operator typically spends $7,000 to $9,000 per hour on a 300ER, with the 777-9 expected to be slightly higher due to the complexity of the GE9X. However, the GE9X has faced its own challenges. In early 2026, a durability issue was identified regarding a seal in the high-pressure compressor. This issue led to a temporary flight test slowdown, with only 2 of 5 test aircraft flying in February 2026. While Boeing maintains this will not delay the first delivery in 2027, the long-term reliability of these ultra-high-pressure engines remains a concern for launch customers like Emirates and Lufthansa. Pavement dynamics, ACN, ACR, and CDF analysis. A hidden specification critical to airport planning is the impact of the aircraft's weight on the physical life of the runway. This is measured through the Aircraft Classification Number, ACN, or the Newer Aircraft Classification Rating, ACR, the pavement-friendly giant. Despite its 575-ton mass, the A380 is famously pavement-friendly. This is due to its 22-wheel landing gear configuration, which distributes the weight more broadly than the 14 wheels on the 777-9. The A380's main landing gear, MLG, consists of 2 6-wheel body gears and 2 4-wheel wing gears. The cumulative damage factor, CDF, analysis shows that the A380's wide gear track, 12.5 meters between wing gear axles, places the heaviest loads on the sections of the runway that are rarely used by other widebody aircraft. Standard long-range jets, like the 777-300ER, have tracks between 10.6 and 11.9 meters. Consequently, the A380 contributes roughly 30% less to the peak pavement damage of a typical fleet mix than its gross weight would suggest. 777-9 pavement stress and ACR values. The Boeing 777-9, by constant, concentrates its 352-ton taxi weight onto 2 6-wheel trucks. To support this weight, the 777-9 uses higher tire pressures, 229 psi, than the A380, 218 psi. Higher tire pressure leads to higher vertical strain in the upper layers of the asphalt, potentially accelerating pavement cracking. The deal breaker here for small airports is that while the 777-9 fits in the gate, it may require runway strengthening if the subgrade is ultra-low, category D, as its ACR exceeds the PCN of many secondary airports. Cabin environment and psychoacoustics. Passenger experience is often marketed through luxury, but the true differentiators are noise levels, cabin altitude, and humidity, factors that directly influence jet lag and fatigue. The A380 noise advantage. The A380 remains the quietest large aircraft ever built. Measurements show that at cruise, the A380 mid-cabin noise level is approximately 68 dB, compared to 73 dB of the 777-300ER and roughly 70 to 71 dB for the 787 and A350. Because the decibel scale is logarithmic, a 5 dB difference represents a nearly 300% difference in sound intensity and 25 to 30% difference in perceived loudness. The A380's noise profile is also flatter, lacking the high-frequency hiss of airflow found in twin jets. This makes it the perfect aircraft for ultra-long-haul premium travelers. 777X atmospheric improvements. The 777X counters the A380's quietness with superior cabin atmosphere. By utilizing the 787's environmental control systems, the 777-9 maintains a cabin altitude of 6,000 feet, even at a flight level of 41,000 feet. The A380, designed with older aluminum alloys, typically maintains a cabin altitude of 7,000 to 8,000 feet. The 777X also features higher humidity levels and advanced filtration, which reduces the dry eye and dehydration symptoms common on the A380. Economic deal breakers. The cargo revenue gap. The most profound hidden specification that led to A380's commercial failure is the cargo-to-passenger ratio. Airlines generate a significant portion of their profit from belly cargo, which subsidizes the cost of the passenger flight. The A380 is a volume-limited aircraft. Its double-deck configuration uses up almost all the internal fuselage volume for passengers, leaving very little space for freight. The A380 provides approximately 133 cubic meters of cargo space, while the 777-9 provides a massive 230 cubic meters. On a route like Dubai to New York, JFK, an A380 burns roughly 65 tons more fuel than the 777. To carry potentially only 100 extra passengers, this makes the A380 economically unviable on any route where it cannot maintain a passenger load factor of at least 85%. The 777-9, with its high cargo capacity, can remain profitable even with a 60% passenger load, because the belly freight covers the fuel bill. The A380neo, engineering realities and failure. The A380neo new engine option was a proposed upgrade meant to bridge the efficiency gap between the A380 and the 777X. However, the project was never launched due to a series of technical and financial death spirals. To achieve a 10 to 15% fuel burn reduction, the A380 requires modern engines like the Rolls-Royce Trent XWB or a D-rated GE9X. These engines have significantly larger fan diameters, 118 to 134 inches, than the original Trent 900, 116 inches. The heavier engines would increase the bending moment of the wing, requiring hundreds of kilograms of structural reinforcement. To maintain ground clearance for the larger nacelles, the landing gear would need to be lengthened, adding even more weight. Larger nacelles increase the wetted area and form drag, which would negate about 2 to 3% of the engine's efficiency gains. Airbus calculated that the OEW, operating empty weight, increase would be so significant that the Neo would only offer a 5 to 10% net improvement in fuel burn, not enough to justify the $3 billion development cost. Engine manufacturers like Rolls-Royce were unwilling to invest in a backspoke engine for the A380 when the total remaining order book was so small. Unlike the A320neo, which had thousands of orders, the A380 was a one-customer aircraft, Emirates. Developing an engine for a fleet of only 100, maybe 200 aircraft was commercially impossible for the OEMs, especially when they could focus on the A350 and 787 markets, where thousands of engines would be sold. System architectures and hidden specs. Beyond the airframe and engines, the internal systems of this aircraft represent two different eras of electrical and hydraulics engineering. Hydraulic pressure 5000 psi versus 3000 psi. The A380 was the first commercial aircraft to utilize a 5000 psi, 35 megapascal hydraulic system, a significant jump for the industry standard 3000 psi. High-pressure hydraulics allowed Airbus to use smaller, lighter actuators and thinner titanium piping to move the massive flight control surfaces. This saved approximately 1000 kg in weight. The 777X maintains a hybrid approach, but relies more on electromechanical actuators for secondary systems, reducing the reliance on heavy hydraulic fluid lines throughout the cabin. Electrical generation. Variable frequency versus constant speed. The A380 utilizes 450 kW variable frequency generators. By allowing the generator frequency to vary with engine RPM, Airbus eliminated the heavy and maintenance-intensive constant speed drive (CSD) found on older jets. The 777X takes this further, utilizing a 787-style, more electric architecture, where the auxiliary power unit (APU) and main engines provide massive electrical reserves to power the environmental control systems (ECS) without the need for traditional bleed air from the engines. This no-bleed or low-bleed approach improves engine efficiency by 2–3% by not siphoning off high-pressure air from the cabin. Operational resilience, fact check and 2026 outlook. As of February 2026, the status of both programs has been affected by the global recovery and technical setbacks. The 777X program is currently 6 years behind its original schedule, with the first delivery to Lufthansa now expected in second quarter of 2027. The FAA and EASA have increased their oversight, requiring a phased type inspection authorization that has slowed progress. Despite this, the order book has remained resilient, with Emirates adding 65 more 777X units at the Dubai Air Show 2025, bringing their total commitment to 270 aircraft. The A380 has defined early retirement predictions. As of April 2024, there were 189 aircraft in service with 10 operators. By 2026, the global fleet valuation has actually increased by 2.8%, as airlines realize they cannot meet post-pandemic demand without the super jumbo's capacity. Emirates plans to fly the A380 until 2040, investing in massive cabin refurbishments to keep the fleet modern while waiting for the 777X. Maintenance and life cycle costs. Maintenance costs are the ultimate hidden spec that determines the long-term viability of an airframe. The deal breaker for many AC-rated operators like Air France and Thai Airways was the sunk cost of point-to-point operations. By the time an AC-rated is turned around and ready to fly, the airline has already spent nearly $500,000 in fuel, staff, and landing fees. On a twinjet, these fixed costs are significantly lower, providing the airline with more exit liquidity if a route underperforms. Now share your thoughts in the comments. Maybe you know more interesting hidden specs. I'll be really interested to hear your opinion. Don't forget to like and subscribe. But now let's meet